Yeah, so this is, I'm going to be talking about, in a way, this is kind of a summary of my lectures, but let me just say something personal first, which is that, you know, my father was a physicist, and in fact, he went on sabbatical to San Carlos when I was 7 years old, so I spent a blissful half a year going to Brazilian schools, and I learned to speak Portuguese. I've forgotten everything now. But even beyond that, you know, both before and after that, I grew up in Salt Lake City, Utah, which is not a very international place, especially when I was growing up there. And, you know, at my parents' house, there were always people from all over the world coming to visit. And so they would come to dinner and they would argue. They would argue about everything from politics, also something called physics, which I totally didn't understand. And I also saw that my father was the only father that I knew that was wearing shorts to work. And so long before I knew what physics was, I wanted to be a physicist, okay? And the part of physics that's really especially near and dear to my heart is actually the aspect that it's such an international field and there's so much international collaboration. So being here, this place is all about that, right? This is 100% exactly devoted to the aspect of physics that, in a way, is the nearest to my heart. So for me, this is really a tremendous honor to be here, and I'm really glad for this opportunity. So I'm going to give an overview of what I see as what did we learn when the Higgs was discovered, and where does that put us now in an intellectual way with regard to the Standard Model? So this is somewhat of a personal view, and I'm only going to be looking at certain aspects. There are other aspects that are also important, I'll mention briefly, but I want to dig into one specific aspect of this, which I think is one of the deepest and most difficult conceptual questions that I know in physics, okay? So this is the outline of my talk. I'm going to try to argue that scale hierarchies, the fact that we have physics going on at very different scales, is not just a fact of life, but it's actually one of the main reasons we're able to do physics at all, okay? And we rely on approximations of neglecting some scales and focusing on other scales, and that's how we've been able to make progress in physics. And the Standard Model, or quantum field theory, is no exception to this, okay? So it's not some highfalutin field that operates by a different set of rules from the rest of physics. So in a sense, I want to bring it back to Earth. So I want to explain that point of view. Then I'm going to go over some aspects of the Standard Model of particle physics from this point of view to talk about its tremendous successes and also what I call the hierarchy paradox, okay? And I'll explain what that is. And then at the very end, actually I'm going to spend most of the time on this. At the very end, I'm going to just briefly mention some of the ideas that people have been led to trying to understand this hierarchy paradox. But I'll spend most of the time trying to convince you that there really is an interesting paradox, because these ideas don't actually work very well, okay? And so it's really an open question, so I want to spend more time on the question than the proposed answers. Okay, so this is all relies on this Higgs boson discovery, almost exactly, what, 22 years ago now? Okay, and so this was on the front page of the New York Times, this photo. This is the CERN auditorium, and these are the plots that were shown at this talk, and these bumps constituted the main evidence for the Higgs boson, okay? So what did these bumps teach us about the universe? That's what this talk is about, okay? So first, some very, very general statements. I claim physics is possible only because we don't have to know everything, right? Thank goodness, okay? And in fact, most of the time, the thing that we don't have to know has to do with a hierarchy of scales. This is what makes physics possible. So let me give some very elementary examples, right? One is the multipole expansion of classical electromagnetism. So if I have some charges confined in some region A, but I want to know the electrostatic potential some distance r away, which is large compared to A, we know that we can expand it in multipoles. And if we have some generic charge configuration confined in the distance A, we would expect the nth multipole to be suppressed compared to the 0th multipole, the monopole, by a factor of a to the n. And that turns this into an expansion in powers of a over r, right? So this is very familiar. And so if we're at distances much larger than a, then we only need a few multipoles to describe what's going on. In a sense, we have a theory with only one or a couple of parameters, right? And that is universality, right? That's why we're able to study things that, may be very complicated at short scales, but we can understand how to do the electromagnetism of these things because it's universal at long distances. On the other hand, if we manage to start probing at distances of order A, then of course this expansion completely breaks down, but we know how to interpret that. We just say, well, that means I actually need to know what's going on here now, okay? I'm not trying to sum this to all orders or do something weird like that. I just realize I just need a new description that tells me what's actually going on in here, right? And so we interpret this when we see these infinitely many parameters happening in a theory in a case like this. We interpret this as saying, this is great. We're starting to see, uncover something, a more fundamental theory. And we believe that that theory will be simpler. Okay, and I don't know, I can't prove that that works, but it's certainly done pretty well for us so far. And so what might we discover if we start looking in here? I don't know, we might discover atoms, for example. We might discover atomic structure, okay? So this very simple example, I think, is kind of a paradigm for many things in physics. So for example, classical fluid mechanics, we know that the microscopic picture is some molecules bouncing around, okay? But if we're looking at times, if we're measuring over times that are long compared to the collision time and distances that are long compared to the mean free path, then what we find is a universal behavior, right? And these terms, the sort of so-called perfect fluid terms, are universal. They don't really care what kind of molecules we have. And the higher order terms, like viscosity terms, actually start telling us something about the structure. Is there a problem? You don't know? Yeah. So far it's going well for me. I don't know. Okay, all right. Okay, and so this is a little more like the kinds of theories we're interested in particle physics, right? There's some sort of microscopic description, we have some sort of equation of motion, but ultimately we know it's doomed. There's some more fundamental microscopic description. So in the late 70s and 80s, largely due to the work of Ken Wilson, this kind of idea was developed as a paradigm for quantum field theory, okay? And so in this sort of Wilsonian paradigm, we think of a quantum field theory as some approximate or effective description of a system that has many quantum degrees of freedom. So the paradigmatic example of that would be a lattice of quantum spins. If you sort of zoom out, you just see it looks like a continuum of quantum degrees of freedom. But of course, there's a scale A where you start seeing individual spins, okay? And because we're dealing with quantum mechanics, long distances are equivalent to low energies and low momenta. So what I want to claim is that in the quantum field theory, as well as in these other areas of physics that are maybe more familiar to us, if we want to have a predictive theory, we must have a hierarchy of scales, right? The quantum field theory that describes some lattice, that theory will break down at the scale of the lattice spacing, and then you have to know the details of the material, right? Okay? And similarly, in any quantum field theory, generically, we would expect there's some scale m where the theory breaks down, and the theory is only predictive for, I'm going to use energy because I'm a high energy physicist, okay? So my preferred variable is energy, but at low energies, we are able to get some predictions, but we expect it to break down at some scale m, okay? And so in a relativistic quantum field theory, of course, energy can be converted into mass, and so that means we can only describe light particles, right? Particles with mass below this energy scale that we're probing, okay? Now, hierarchies are, of course, a fact of life, right? We've explored many orders of magnitude already in just about every field of physics. So in particle physics, this is sort of a cartoon of the energy scales that we've probed, right? So the EV scale is atomic physics. We go up 3 orders of magnitude, we see nuclear physics. Then at 1 MeV, we start seeing relativistic electrons and quantum electrodynamics. At GeV, we start seeing effects of the strong interactions in QCD. And the TeV scale is where the standard model, just below the TeV scale, the standard model comes into full bloom. So some of the particles that we have the electron, the proton is right around the strong interaction scale. And these crucial players in the weak interactions are just below the TeV scale, okay? And of course, the reason that this is an exciting field to be in is that currently the Large Hadron Collider is exploring scales just above the TeV scale, okay? All right, and so now what I want to tell you is that, so there are many orders of magnitude here, there are many hierarchies, and I want to tell you that all of these hierarchies within the standard model are natural and well understood. That's what I'm going to be doing the next few slides, okay? On the other hand, as soon as we say, okay, let's go up to the next level, PeV, or maybe even a higher scale, as soon as we try to do that, we run into paradoxes. So the same thing that has worked for generations and enables us to understand all of this stuff in a nice way fails as soon as we start to go up here. That's the message that I'm trying to tell you, okay? And the sort of key word here that I've sort of hidden from you a little bit is natural. What do I mean by natural? What do I mean when I say I understand this? I don't mean that I can predict all of these numbers. I can't, and neither can anyone else. So I'm going to have to explain to you what I mean by natural, and maybe well understood is overselling things a little bit. But anyway, I'm going to explain to you what I mean by this, okay? And you can judge for yourself, okay? So I think the best way to explain what I mean by naturalness is to give you some examples of unnaturalness, okay? And there are plenty of examples of this in physics. It's a very well-known phenomenon, and so I'm going to give some examples. So the simplest, maybe most canonical example would be quantum spins on a lattice, okay? So these S are spin operators that live on the sites of a lattice. This is the Heisenberg model, okay? And I have some nearest neighbor spin coupling. And if J is positive, this wants the spins to align, okay? So this is like a quantum version of the Ising model. You can think of it that way, okay? And if I just look at this system at generic temperatures, okay, then I can ask sort of quantum field theory-like questions. In quantum field theory, I'm interested in calculating correlation functions. What's the correlation function of a variable here multiplied by a variable here? So this here would be a spin two-point function. Okay, so there's a t equals 0 here. That should not be here. This is meant to be at generic temperatures, okay? So the first typo, I'm surprised it took this long, but anyway. Okay, so at a generic temperature, the claim is that as a function of the distance between the 2 points that I'm looking at, this correlator decays exponentially, okay? This is what happens at generic temperatures. And this scale that appears in the exponent is the correlation length. It tells you roughly over what length are the spins correlated with each other, okay? And the fact that for a generic temperature, the correlation length is of order A is telling you that there is no hierarchy of scales here, right? If you want to learn anything about this material, you just have to study the details of this lattice model, okay? There's no hierarchy, there's no sort of universal behavior that looks like quantum field theory or anything. But this theory has a phase transition. If I go to a certain very special temperature, the critical temperature, then the system has a second-order phase transition. And at a second order phase transition, this correlation length xi diverges, okay? And in fact, it's known that its behavior is governed by this kind of an equation. This is a critical exponent equation. These equations were discovered in the late 70s by Ken Wilson and other people, condensed matter people as well. And so what this is telling you, notice it's normalized to A, so it's telling you that if you want to have a correlation length that's much larger than A, so that we can somehow use some universal long distance description, I have to tune the temperature very close to the critical temperature. This exponent is some number, it's a rational number, it's not an integer, that at least, yeah, in this model it's certainly not an integer, but it's some positive number of order 1, okay? So this is a very simple and well-known type of example where if we want to have a very large correlation length compared to the microscopic scale, we have to tune a parameter, namely the temperature, okay? Now, the quantum field theories that we're interested in for fundamental physics don't have a temperature. I mean, there's a tiny temperature in this room, there's a little tiny temperature out there in the cold of space, but that doesn't do anything very much. We're basically at 0 temperature, right? I'm interested in what happens at 0 temperature. But in fact, there are also phase transitions at 0 that occur at 0 temperature in condensed matter. In fact, the Coop rates, which is one of the hottest topics in condensed matter physics right now, one of the things that makes them interesting is that they have phase transitions at 0 temperature. Okay, and so for example, there's this antiferromagnetic phase, superconducting phase, I forget what FL stands for, and the reason that this is not an experimental plot is that actually these phase transitions are not very well understood, okay, especially by me because I'm not a condensed matter physicist. But I'm going to take some poetic license and just assume that this phase transition here is a second order phase transition, okay? I don't know if that's true. I don't even know if that's compatible with what is known, but let's suspend disbelief, okay? So what is this doping fraction? This doping fraction is you have some material that has some basic structure and you introduce some impurities, right? And this is a fraction, the fractional amount of this impurity. And I think the impurity is copper, if I'm not mistaken, which is why these are called Coop rates, I think, but I'm not sure. Anyway, it doesn't matter, okay? So experimentally, how would you explore this? An experimentalist would have to prepare a sample with different amounts of doping, and then if they could cool down to very, very close to 0 temperature, they could hope to see some signs of this phase transition, right? But they would have to compare different values of this X. Now this is a lot more about the way that quantum field theory works, right? Because there's some fundamental Lagrangian that comes from, I don't know where, string theory or something, and it fixes the parameters, and I don't really understand it, but there are a lot of parameters that it fixes. So this doping fraction here is just kind of a parameter like that that's fixed by the experimentalist. But again, now, if this is a second order phase transition, I would expect the correlation length to diverge at x equals x star at this magic value right here. But again, if I want a large hierarchy, I have to tune the doping fraction, right? And that's not an easy thing to do, okay? All right? So these are examples where if I want a hierarchy, I have to fine-tune, I have to finely adjust some fundamental parameter or more fundamental parameter, okay? And in this case, literally, if I do manage to do this tuning, so assuming this is a second order phase transition, then the long distance physics of this is actually described by an effective quantum field theory, okay? Albeit not a relativistic one, not even not a relativistic one, not Lorentz invariant, but a quantum field theory. Okay, so now let's talk about the mass hierarchies in the standard model. As I showed you, there are plenty of hierarchies in the standard model, so the question is, do any of those have this kind of unnatural character that I've just shown you, okay? And let's start with the biggest hierarchy of all. We believe that the photon is exactly massless, okay? So that's an infinite hierarchy compared to any other mass, so let's start with that. Is that natural, okay? Well, a massless photon actually has 2 helicity states, right? Those can be thought of as the 2 circular polarizations of a classical electromagnetic wave. When you quantize those, you end up with 2 photon helicities, okay? And this is just, in the quantum theory, this is just a fact about the representations of the Lorentz group. On the other hand, a massive photon has 3 possible spin states. As you know, because for non-relativistic quantum mechanics, if the photon had a mass, there would be a frame where it's at rest. And then it would be some spin 1 particle, and it has 3 possible spin states, okay? And you can see that there's no way I can just tune some parameter in some UV theory that when it crosses some threshold, the photon goes from having 2 degrees of freedom to 3. That doesn't make sense. So it's clear that a massless photon is completely robust just because 2 is not equal to 3, right? If you're tuning some continuous parameter, you can't make something just jump discontinuously, okay? So, but there are lots of other particles where the number of degrees of freedom doesn't change when you turn their mass on and off, and those would be fermions, okay? So it turns out that if you take a fermion and you make it massless, it doesn't have any difference in the degrees of freedom, so we can't use the photon argument, okay? So what about, say, the fact that the electron is much smaller than the muon mass, okay? Well, it turns out that we don't change the number of degrees of freedom as the electron mass goes to 0, but we do get an extra conservation law. So the helicity is the component of the spin along the momentum, and it turns out that in the massless limit, the helicity is either +1/2 or -1/2 for fermions, and it's conserved. Basically, what it means is that the EL, we can think of these, the plus helicity ones as right-handed electrons and positrons, and the negative helicity ones as left-handed. And we can really, in this massless limit, we can think of the left and right-handed particles, components as independent particles. And the number of E rights and the number of ELs is separately conserved. So there's an additional symmetry, okay? And so this symmetry is exact if the electron mass is 0, but you can imagine that this makes it robust. If the electron mass is in some sense small, then I can just explain that by having an approximate symmetry like this. And as long as that approximate symmetry survives in my more fundamental description, it gives me a perfectly sound reason why the electron mass could be small, say compared to the muon mass, okay? And this criteria that a small parameter, if you have a parameter and you get an extra symmetry when it goes to 0, if you develop a symmetry, then it's always natural to have that parameter be small. This is 't Hooft naturalness. One of the fathers of our field who did so many things for us also taught us this lesson, okay? And so this mechanism that I just described works for all of the fermions in the standard model, so at least there's no apparent mystery about them, okay? The masses can be whatever they want. There doesn't seem to be any mystery about it, okay? But now there's another kind of particle. I'm using the proton here, and I guess I shouldn't have said all fermions. The proton is a different sort of a beast because it's a composite object, okay? So that's a hadron generated by the strong interactions. So anyway, I'm going to talk about the proton, or I could talk about any other massive hadron or rho meson or something. Why are they small compared to other masses like the W mass or even larger masses? Well, here's what we understand about where the proton mass is coming from. The theory of the strong interactions is quantum chromodynamics, and famously, there's a dimensionless coupling constant that characterizes the strength of the coupling, but that coupling constant depends on the energy scale at which you measure it. And it's weak at the coupling is small at high energies, and it becomes strong at low energies. And when it becomes strong, then all sorts of miracles happen. I mean, all sorts of non-trivial things that we don't fully understand, and that generates the hadron spectrum at a scale of around a GeV. So that's the left part of this plot. That's where the coupling is getting strong, and that's where all these things are happening. And even though we don't have a pencil and paper understanding of this, this shows the data that gives an extremely accurate, here's the value of the strong coupling evaluated at MZ, and one of the most precise points is this one right here, which comes from lattice QCD, so it comes from numerical simulations, and this is actually, one of the most precise determinations of this, but all of these things are very consistent with each other, including very precise measurements at high energy. Yes? That's what I'm going to explain. That's what's symmetry breaking small?
So, well, first of all, you didn't tell us what the symmetry was. You said the symmetry is somehow that you want EL and ER to be separately conserved.
Yeah, it's a U1. So for the experts, I have a left-handed Weyl fermion field and a right-handed Weimer fermion field, and the symmetry is just where they rotate in the opposite way. That's the one. This is the axial symmetry that acts only on electrons.
Right. So we know the symmetry is broken, right?
The symmetry is broken by anomalies, and that effect. This has an anomaly, with electromagnetism. Okay, but that effect is too small. There's some technical details that I'm suppressing here. This is not a class on quantum field theory. This is an overview, and so I am omitting some details. But the end of the story is that this symmetry guarantees that the electron mass, if this symmetry was exact, the electron mass would be 0. That's a true statement. So.
Okay, yeah. I'll ask.
Yeah, we can talk about it more. I'm happy to talk about more details, but I think I really don't really want to get into technicalities here. Okay, so in this case here, the real question is not about the proton mass or the rho mass or whatever. The question is, what about the scale lambda where this coupling becomes strong, right? That's what governs this M proton. Why is that scale small compared to the W mass or other masses that I might think about? And this is actually not hard to understand, because if you express this scale in terms of the input parameters of the theory would be this gauge coupling here, which is a coupling. It's analogous to E, the electromagnetic coupling E. It's the same kind of thing, except for a non-abelian gauge theory. And so what you need, because this lambda depends in this exponential way, like e to the minus 1 over the coupling squared, and there's this factor of 16 pi squared here. If you have, for example, that this coupling is of order 1 at the TeV scale, then you get a GeV. So the point is that for order 1 input parameters, because of this thing here, you get a very small number out in a natural way. Okay? So that doesn't allow us to predict exactly what lambda QCD is, but I think it tells us we don't need to worry about the fact that it's small compared to lots of other scales of physics that we see. Okay? So I want to claim that this is robust and natural. And in fact, this mechanism that you generate a large hierarchy of scales because you have some coupling that's weak and then it becomes strong, but it takes many decades, it takes several decades of energy to become strong, is exactly occurs in the BCS, the classic BCS mechanism for superconductivity. Okay? There too, as actually shown by Joe Polchinski, you can actually really think that there's a certain kind of an interaction between these two Cooper pairs. It's very weak, but as you go towards the infrared, it logarithmically increases, and at some point it gets strong, and it binds the Cooper energy with an energy that's some 3 orders of magnitude below the characteristic scale of atomic physics or condensed matter physics, right? A generic energy level change in a condensed matter system is EV. A Cooper pair has a binding energy of 10 to the minus 3 EV. It's exactly like the binding energy of a hadron. Well, it's very analogous. And we, of course, know that the BCS mechanism is super robust. In many classes of materials, namely metals, you just cool them down enough and you get superconductivity. It is experimentally extremely robust, okay? Okay, so I claim that these two mechanisms, okay, in one way or another, explain all the hierarchies within the standard model, or explain may be too strong a word, but they tell us that having these hierarchies is not a problem. There's no apparent problem in having these big hierarchies, okay? But now we don't know what the more these are cases where I sort of knew the more fundamental theory, and I was able to sort of show you from the top down that you can have a hierarchy, there's no problem, right? But now, in the situation with the standard model, we of course don't know what's above the standard model. What is the more fundamental theory, okay? We have some guesses, but we don't really know. So we have to learn to think about this question from a bottom-up point of view, where we don't know the fundamental physics, okay? And so I'm going to talk about that. How do we think about effective field theory from the bottom up, okay? And we'll be testing this picture. We can test it in these examples where we do understand it also from the top down, right? Okay, so the first things first, dimensional analysis is going to be super important. And so I'm using particle physics units where h bar and c is 1. And that means everything can be expressed, any physical quantity x has units of mass to some power, and that power I'm going to call the mass dimension and going to denote it by this bracket, okay? Okay, and so then, what does an EFT look like? So for the next few slides, I know this is a colloquium, and I know I'm not supposed to write Lagrangians, but I am. And so, but you don't need to know all you don't need to understand exactly what these means. The important thing is going to be that a Lagrangian consists of a sum of operators, okay? And these operators are things like scalar squared, they're fermion squared, field strength squared. They're made out of the fields and derivatives of the fields, okay? And there's, in principle, we can include any Lorentz invariant operator we want, okay? And these operators all have some mass dimension O, okay? And the Lagrangian has a mass dimension 4, and so I'm factoring out the mass dimension parameterized by some scale m, okay? And making every coefficient dimensionless, okay? And so now, if you do some dimensional analysis, if you say, okay, let me pick one of these terms, let me pick my favorite O, okay? And now I'm going to see when is this O negligible? And the way to answer that question is, if you want to know whether something is negligible, try setting it to 0 and then perturbing in it and see what you get, okay? And if you get small corrections, then you know it's perturbative, right? So just do that, and I claim that the answer is determined just by dimensional analysis, okay? Because if you look at the fractional correction to some observable that you've set, where you first of all set the coefficient to 0, and then you look at the fractional correction when you turn on this coupling, CO at linear order, because the C comes with some number of powers of n, okay? Oh my goodness, oh, there's some terrible, there's some horrible typo here, okay? So, no, actually it's okay. Okay, and so basically the point is that depending on whether the dimension of O is less than or greater than 4, the m's are going to appear in the numerator or the denominator, right? Because you just see that, you know, for O, the dimension of O less than 4, the m's appear in the numerator, whereas for the dimension of O greater than 4, they appear in the denominator. That's it, okay? That's really all there is to this. And so the point is that if the dimension of O is less than 4, then these terms become more and more relevant at low energies. Okay, so E observed is some energy scale associated with the quantity that I'm trying to calculate. Whereas if the dimension is greater than 4, the terms become less and less important at low energies, so we call these respectively relevant and irrelevant. And if the dimension is equal to 4, then there's no energy dependence, and we're just doing an expansion in the powers of the dimensionless coupling, okay? So just from this very simple observation, we see that actually only the relevant and marginal interactions are important at sufficiently low energies. If I go to sufficiently low energies, I can ignore all these irrelevant interactions. And these are meant to be, these are technical names, okay? So they're not totally irrelevant, but you can see where the name comes from. But it's a wonderful fact that if I include just the marginal and relevant interactions, that's exactly what people used to call a renormalizable theory. So in the old days, people thought that only renormalizable theories made sense because only in those could you, quote unquote, remove the infinities, okay? But that's not the modern point of view. The modern point of view is just we have a low energy expansion, and those are the dominant terms. That's it, okay? This was one of the things we learned from Wilson. Okay? Okay, so now let's use as my favorite example of an effective field theory is, of course, the Standard Model, okay? And so what is the Standard Model defined as an effective field theory? So I have to assume the particle content of the Standard Model. I don't understand why it is what it is, so that's an input, okay? So there are 3 generations of quarks, 3 generations of leptons, neutrinos, some force carriers, and at the very center, very importantly, the Higgs, okay? And these force carriers, like the photon, for example, we know the photon is associated with some gauge invariance, okay? And so that gauge invariance is necessary to have a photon that is massless and has only 2 degrees of freedom. And similar statements for these other force carriers of the strong interactions and the weak interactions, okay? And so those are just assumed. I also assume that the theory is Lorentz invariant. And then with those restrictions, I just write everything down that I can, okay, that has up to the dimension 4 terms. And actually, I'll keep going, okay, but I know that these are going to be a lot smaller. So what do I have, okay? So I have exactly 2 relevant terms, okay? And this is a general thing. It has to do with the fact that if you look at the dimensions of the fields and the derivatives, they all have positive mass dimensions. Okay, so you can make the mass dimension as big as you want just by stringing fields and derivatives together, but there are precious few operators that are relevant, okay? So in fact, there's only 2 relevant operators. One of them is a constant, and you might think, well, adding a constant to the Lagrangian doesn't do anything, but in the presence of gravity, it does. It's a cosmological constant, okay? So that's a relevant term, and in fact, it has dimension 0 because it corresponds to the identity operator. Then the next operator is, guess what, our friend the Higgs. So this H is a Higgs field, and there's a mass squared term for H dagger H, okay? This is not literally the mass of the Higgs. This tells you the curvature of the Higgs potential at H equals 0, okay? But it's a very important relevant parameter in the Standard Model. Then there's a whole bunch of marginal terms. I'm not going to write them down, but I'm going to tell you a little bit more about them in a bit, and then there are irrelevant terms, okay? Now, what do we know about the relevant terms? Well, we actually know them very well, just experimentally, okay? Because, first of all, we know exactly what this term is because this is supposed to explain, the Higgs potential is supposed to explain the W masses, the Z masses, and the mass of the physical Higgs itself, and that completely pins this thing down, and it's some number, which I'm not bothering to look up. It's a very specific number, but it's around 100 GeV squared, and that's the typical mass scale for the heaviest particles within the Standard Model. Okay? So we know this very, very well, but we actually know the cosmological constant as well, okay? So, because it's currently driving the expansion of the universe, okay? Unless you believe in some nutty cosmological model, which is fine if you do, okay? But if we don't do that, if we just assume we have just this theory, gravity plus the Standard Model, then we know what this is, and again, we know it pretty accurately. But I'm giving you the orders of magnitude. And notice I've expressed it in the same units as the Higgs mass, and it's some 53 orders of magnitude smaller in those units. Okay, so it's really small, okay? And the real smallness of this is driven by the fact that the expansion of the universe is very slow, right? It's expressed in GeV units, it's some ridiculously small number, okay? So we don't understand why these are small, okay? I'm not saying that, and in fact, that's the problem, I'm going to argue in a little bit, okay? But for now, let's just say, I'm not worrying about that, okay? I want to have a hierarchy so I can do physics so that the Standard Model is predictive, so I just need these coefficients to be small. That's it, okay? But really, especially this one, super ridiculously small, okay? Yeah, just a comment. I just want to make sure it's clear, right? when I talk about the hierarchy problem, it's not a problem of small numbers. We have plenty of small numbers in the standard model. I do not lie awake at night worrying about them, but we're going to see that I'm trying to convince you that you should be lying awake at night worrying about these numbers, okay? But I haven't done that yet. Yes? What's that?
Are you requiring unitarity? You just said there is.
Unitarity actually comes for free in the sense that, if I make this assumption here, the theory is unitary up to exponentially high scales. No, I'm not including the dimension 5 terms. I'm going to talk about these in a little bit. I will make you happy, okay? But I'm not going to talk about them right now because I get to decide the order that I'm talking about things, okay? Okay, so is the standard model a good effective field theory? Okay, that's the question I want to ask. So I can't possibly review the physics of the standard model in a few minutes, but I'm going to tell you some highlights, and I hope you believe me, this is not fake news. So I'm going to tell you, if we just write down the most general marginal terms, okay, and you fit them to data, what do you get? Okay? First of all, without doing any fitting, you just find automatically that even though you didn't require it, you automatically have baryon and lepton number conservation. The second thing is that you have these Yukawa couplings, which determine the masses of the fermions, the electrons, quarks, and so on. And these beautifully explain the incredibly intricate pattern of observed flavor and CP violation, okay? So there have been literally decades of work on experiments, doing many, many measurements. There are entire thick books like this full of data about them. This is just one plot that shows you lots and lots of different observables all converging on this so-called unitarity triangle. These 3 points are the area of this triangle is representing the amount of CP violation in the standard model. It's a single number, and all these different bands are different determinations of this that all agree with each other, okay? And there's much, much more than this, okay? It's incredible. It's really incredible. The other great success of the standard model is that it predicts the neutrino mass is 0. Are you awake? Okay, that doesn't sound like a success, right? In fact, you may go to talks and say, the standard model is wrong, the neutrino mass is non-zero. That's because it's 0 when I only include the marginal terms, okay? If I start including irrelevant terms, okay, then the very first thing I hit is dimension 5 operators, and there's only one kind of dimension 5 operator that you can add to the standard model. It looks like this. It involves the lepton fields and the Higgs fields. Okay? And it gives you a neutrino mass, and this scale m, because it's dimension 5, I have a 1 over m here, and the neutrino mass is of order 100 GeV squared over m. So this beautifully explains why the neutrino masses are much smaller than all the other fermion masses. Okay? There are other possible mechanisms for neutrino masses, just like there are crazy cosmological models. The other models for neutrino masses are not as crazy as the crazy cosmological models, but anyway, I would still count this as a success. Yeah. It's kind of arbitrary because there's certainly a hierarchy among the neutrino masses, but I put a number here just to give you an idea that this is an extremely high scale. This is not, if you just sort of put in sort of order 1-ish numbers or the same kinds of numbers that you see in the other Yukawa couplings of the standard model, you land on quite a high scale. But you shouldn't take this very seriously. But I'm just saying it would be super exciting if this was 1 TeV, okay? Because then we would be exploring this now at that Large Hadron Collider. So I'm trying to give you a sense that it looks pretty far away. We could still get lucky. There are models of neutrino masses where we get lucky and we see something, but it's not indicated, it's not forced on you. Okay, that's the only reason I gave that number. Yeah.
You said that this is the only term that you can add to the standard model? Why is that?
At dimension 5.
Oh, at dimension 5.
At dimension 5, yeah.
Oh, okay,
So, you know, actually, I probably should give this as an exercise, okay? You know, you should figure, I'm going to give you various operators like this, and you have to figure out how to contract all the indices, okay? And then you'll understand why you can't write other things down and so on. But yeah, it just comes from trying everything. Okay, people have classified these operators. It's not trivial, but it can be done. Okay? Okay, and then at dimension 6, you get a whole zoo of things, okay? You get many, many things, and I'm not going to talk, I'm going to just give you some highlights of them. So one kind of thing that you get, for the first time at dimension 6, you can get things that violate baryon number. Actually, this violates lepton number already, but it preserves baryon number. So this operator, for example, allows the proton to decay to a positron, right, which sounds like bad news for us, okay? But fortunately, we already know experimentally that this lifetime is much longer than the lifetime of the universe, so you're not in any danger of decaying, okay? And in fact, this is perfectly compatible with those bounds if you take the scale to be very large, okay? All right? And you might say, wow, this is really big. It's even bigger than the Planck scale. Should I be scared? Should I be scared of some inconsistency? Well, remember the criteria of 't Hooft naturalness. If you get an extra symmetry when you set things to 0, it's natural for them to be small, okay? So these terms could be much smaller even, okay? We don't know, okay? So there's nothing to worry about here, so, okay? But now I should really look at the terms that at dimension 6, there's a whole bunch of terms that I can't forbid by any symmetry whatsoever. They're allowed by all the symmetries of the standard model. There's no reason they should be suppressed. And I've just written 4 of them down, okay? And please don't ask me why they're called T, S, W, and Y. It's a weird historical story. But there are 4 of these that are particularly important. These 4 that I've schematically indicated here, okay? And the point is that there was this fantastic program of precision measurements at LEP, the Large Electron Positron Collider at CERN, from the 1990s through the 2000s. And one of the things they did is they sat right on the Z mass and performed excruciatingly precise measurements of the Z and all the possible decay modes of the Z. And so all of these 4 parameters, for example, are constrained at the level of 10 to the minus 3 if I normalize them by the sort of characteristic scale of weak interactions, okay? So once again, this is all beautifully compatible with the standard model as an effective theory if I assume that the scale m is large, okay? So that's the message I'm trying to tell you, that at least if I ignore the problem, I ignore the tiny values of the coefficients of the relevant operators, the standard model beautifully works, and it's predictive, and as long as the scale m is large, much larger than about 100 GeV. Okay? Okay, so we're about to get lost in the woods, so any questions so far? Okay? Yes?
Can you just repeat this last part about why this part you concluded that relevant and marginal beautifully explained observations?
Well, I'm telling you that is, if you take a whole course on the standard model, then, you will learn about a lot of these things, okay? How the standard model, agrees with experiment for all of these things, how it accounts for the neutrino phenomenology with this term, and also, the fact that these terms make tiny modifications in the electroweak interactions at the level of 1 part in 10 to the minus 3, but these beautiful measurements, that's compatible with these very beautiful measurements. And I'm just saying that all of that is these terms I cannot forbid by any sort of a symmetry, and so it seems that the only way to suppress these would be to take m large. Okay, and that's the generic expectation of effective field theory, okay? And so I'm saying that the standard model seems to be compatible with the generic expectations of, just from phenomenology, is compatible with those expectations, with the major footnote that I'm ignoring the relevant interactions for the moment. I'm just fitting them from an experiment.
Should that be 10 to the 3 times 100 GeV?
Oh, yeah. Thank you. Yes, yes, I'm sorry, because I put the m upstairs, right. I'm sorry, yeah, it should be a factor of 10 to the 3 higher. Perhaps that was confusing. I apologize. Yes, okay? Okay, and so that's what I mean by that, okay? Everything looks great, okay? Okay, but what about these relevant terms? Okay, now I want to come back to that, okay? So let me again just do a top-down example, okay? This is simplified, but it's really the kind of thing that when we ask about, we try to explain things that are not explained by the standard model. We sometimes invent new physics at very high scales. And so here's an example where I'm going to couple a bunch of fermions to the Higgs, okay? And please don't worry that there's 2 kinds of fermions and there's some weird pattern here. That's just details for the experts, okay? It's just a Yukawa coupling of a new heavy fermion to the Higgs, okay? And I'm, for simplicity, giving them the same mass. I don't have to do that, okay? And now the point is that at the one-loop level, okay, I should have written the diagram, but my EduRoam wasn't working when I was doing this, okay? So I can have a diagram like this, where I have a Higgs, and I have these new fermions running around a loop like this. So it's the first, the first sort of one-loop diagram that I get from these interactions. And forget about the fact that this is UV divergent, okay? UV divergence is a big smoke screen, okay? We know how to renormalize, and I know that renormalization isn't that physical, so I've renormalized, okay? I don't have to tell you how I did it. But this m is a physical parameter. It's the physical mass of this particle. This y is a physical finite coupling. It's the coupling of this thing. It's renormalized, blah, blah, blah. And then I find a finite correction to the Higgs mass squared, which is proportional to a loop factor like this. There's 2 factors of y because there are 2 interactions, and proportional to the mass squared of this fermion. That's just the result of an honest calculation, okay? And so you can see there's a danger here, because if this m is sufficiently large, then this term can be bigger than 100 GeV squared, which is somehow what I want the Higgs mass parameter to be, okay? So is this a problem or not? This is a fact that this happens in theories like this. Is this a problem or not? Okay, well, let's put in some numbers to have something concrete to talk about. So I'm going to put in the kinds of numbers that we would be interested in if we were trying to make a grand unified theory. This could be some part of some grand unified multiplet, okay? And so what we want is, then we want these heavy guys to have a mass of around 10 to the 16 GeV. We need these Yukawa couplings to be 1. Why? Because things are supposed to unify, remember? Okay, so we can't just say, oh, I'm going to make y be 10 to the minus 20. Ha-ha. Okay, no, because unification is telling you these couplings are order 1. And then, if you just put in these numbers, you're finding a correction to the Higgs mass squared that in GeV units is 10 to the 30. Okay, again, is that a problem? I don't know, let's see. Okay, so we haven't seen this 10 to the 16 GeV object, okay? So we can write an effective theory where we've integrated out, where we've gotten rid of it, and put its effects into the parameters of the effective theory, okay? And so the effective theory is called the standard model, and in the standard model, the Higgs mass squared has a value in GeV units that's about 10 to the 4. And this contribution that I've calculated, I've only calculated the first loop piece, but then there are higher loop pieces, and it's of order 10 to the 30. Okay? So if I want to know what the fundamental parameter, which is the coefficient of h dagger h in the gut theory, all I have to do is I have to subtract this from this. What could be simpler, right? Okay, first, I actually have to calculate this to 14 loops, okay? So let's say I've done that. I'm very strong. I'm a very good calculator. So then what does this equation look like? See, the reason I have to calculate it to 14 loops is I want to know what this thing is. I want to know if I want to make sure that I'm getting this number out, right? So I would claim I would have to predict this number to all of these digits Actually, the last two I don't, that's a typo. Crap, I've had the zeros here. There's supposed to be, it should be a 0, 0 here, okay? Because I don't actually have to predict the last two digits. But I have to predict all of these digits. Okay, so that's why I need 14 loops, okay? And then what do I get? Well, I get this, okay? And see, notice the error is 55. That's why I said I have to compute it to 14 loops, okay? All right? So, is this a problem? I think, yes, I think it's a real problem, okay? Let me explain why, okay? Because let's just look at the parameter space of this model, okay? Let's, instead of focusing on these one very specific numbers, let's look at the parameter space. So this is the parameter space in the gut theory, okay? So this is the actual parameter space that the gut theory has. So there's the scale m, and then there's the coefficient of h dagger h in the gut theory. And we've just seen that if we want to describe our world, they both need to be huge, like 10 to the 30, and this is a mass squared, and 10 to the 16, okay? And we live here. The standard model lives right at this point. But what happens if we go away from this point? If we go in this direction, we're in a phase where the Higgs VEV vanishes. The order parameter, which is the Higgs field, vanishes, whereas on this side, is non-zero on this side, as it says, and it's 0 on this side. In other words, we are on a phase boundary. Okay? Now, if we're not exactly on the phase boundary, well, we're not exactly, but we're like 26, 1 part in 10 to the 26 is how close we are to this phase boundary. But if we were a little bit away, like here or here, then the physical Higgs mass, the actual scalar Higgs mass, would be of order 10 to the 15 GeV. Okay? It would be off by 15 orders of magnitude. Okay? So in order to get what we observe, we have to be right here on this phase transition line. And I'm sure you've noticed that this is exactly the same diagram that I drew for the Coop rates. Oops, the star is supposed to be here. It got moved somehow. Okay? Right? So we would, just like we would not expect that somebody takes the first sample they make, they measure the correlation length at 0 temperature, and they find that it's 26 orders of magnitude larger than the lattice spacing. I don't think that's very likely to happen, okay? So yes, I would say it's a pretty deep mystery. Why are we sitting right there, okay? It's kind of like walking into a room and you see a pencil balanced on its tip, okay? If I saw this, I wouldn't say, oh, well, you know, it's a consistent solution. What's the problem? I would say, wait a minute, there's some strings, there's some glue, there's something here I'm not seeing. There's something I need to understand, okay? All right. So, there may be some, oh, sorry.
So this problem of fine-tuning, was it only for this typical model where you added this Colloquium, or it could be
No, very good. I thank you for asking that question because I really should have said something about that. It's completely and utterly generic, okay? That's the point. This model is just, all it needs to have is some heavy particle in it, and you will have this problem. It's totally generic, okay? All right, except that people have tried to solve this problem, so people are very much looking for non-generic theories where this doesn't happen. And I will say a few words about that, but I really won't have, I'm already out of time pretty much, so. Okay, so, but that's fine, because as I said, I really want to convince you, more that there's a problem, rather than dazzle you with the brilliant ideas that don't work. Okay, so, in the old days, they used to do science by talking. I still love to do science by talking, so I can imagine, just like Galileo had his 3 characters discussing the laws of motion, there could be an old school quantum field theorist and a more modern effective field theorist, and the old school theorist might say, look, don't bamboozle me with all these numbers and significant digits, because the physical masses, I remember I learned in my quantum field theory textbook that the physical masses and couplings are the parameters with which the theory is defined. And they're just measured, and once we put them in, the theory is perfectly predictive, and there's no problem whatsoever. Okay? And that really, some people still think this way, and I think a majority of people used to think this way, but no more. But what I would say is that, okay, that means that you think there's no way we can ever learn anything about any of the parameters of the standard model. You just measure them, and there's nothing more to say. Unlike in every other field of physics, where it makes sense to ask why things are the way they are, but not in quantum field theory. Maybe that's true. I don't believe it for a second. Okay? Okay. Now, the standard model is very beautiful. Oh my God, this thing was perfectly aligned. There's some misalignment problem here. No, it shows up on my thing that way too. Anyway, there's supposed to be a gap tooth here, okay? So this is a very handsome young man, but he does have at least one flaw, or at least a few flaws, right, as we all do. And so there are definitely many, many flaws of the standard model that I have not talked about. And so this is the one slide where I'm listing some of them, okay? And these are all wonderful things to work on. You can make a career on these things, and they're also deep and interesting problems. I'm only not talking about them for lack of time, okay? But I just want to point out that the problem that I am talking about is unique in that it clearly points to a scale of new physics which is just beyond where we're able to probe things experimentally. Whereas these things, and I certainly don't have time to justify this, I claim that all of these things, we might get lucky and see some signs of these in future experiments, but we would need to get lucky. There's no reason in general why these should show up in any of the current or planned experiments. Okay, it doesn't mean we shouldn't look, but it's a difference. Okay, so now I'm going to ask my wonderful hosts what I should do, because I have sort of one more slide each on a different possible universe. I can go through them pretty quickly in probably 5 minutes. Should I do that?
Sure, sure.
I will do that. This is a lightning tour of not one, not two, but 3 possible universes, okay? So when I was a kid, there was this wonderful game show where people dressed up funny, and they had behind different curtains, they had different prizes. So in the same spirit, I'm going to quickly take you a lightning tour of 3 possible different universes that have been proposed to deal with this problem that I've talked about. Number 1, supersymmetry. Okay, what is it? It's an extension of Poincare symmetry that relates bosons and fermions. I think you've heard about this before, okay? So if we want to implement supersymmetry in the standard model, we have to double the number of particles. For each fermion, like the charm quark, we have to introduce a scalar charm quark, and for each boson, like the W, we have to introduce a fermion. And even that's not quite enough. There are a few more things we have to add. It's a technical detail. Okay? Once we do all of that, okay, supersymmetry relates the Higgs mass, which is our big bugbear, to the Higgs Zeno mass, which is a fermion. And if I just told you that fermion masses are fine, okay? They can be made small by these chiral symmetries like this, okay? That's the lightning review of how supersymmetry works, okay? But we don't see these particles, so we have to make them heavier. Okay? But if we make them too heavy, we just get back the same problem. In fact, that M thing that I was writing down before, it could very well have been a Higgs Zeno. Okay? All right? And so if this mass gets really heavy, it doesn't solve anything anymore. Okay? So very roughly speaking, in order to solve the problem, these twiddly things, these enos and spinos, whatever, they have to be all below roughly the TeV scale. Very executive summary. They have been looked for. They have not been found, okay? So this is a very partial summary of many searches. I think there have been hundreds of searches for supersymmetry, both at ATLAS and CMS. They haven't seen any signals. They keep improving the bounds. What should we think of this? The late, great Guido Altarelli, who always had a pithy, who was a very wise man and also had a very pithy way of expressing himself. Already in the 1990s, he said, the Suzy train is a bit late. And if you give me a beer, I'll imitate his beautiful Roman accent, but just a great man. That was in the 1990s. Okay, that was soon after, well, I would actually like to know if somebody can tell me the exact date of this quote. I wasn't able to find it, okay? But this was during the time of LEP. He also, he died in the 2010s, but these plots were already creeping over this way, and what was his response to that? He said, "It is a time for depression, but not for despair." Okay? Well, a lot of people as you can see from this, a lot of people really wanted supersymmetry to be right. Okay, that's it. Next, composite Higgs, okay? The pion mass, I didn't talk about, but I'm talking about it now. The pion mass is actually very light compared to lambda QCD, or the rho mass, or the proton mass, okay? This is natural, okay? Why? It was discovered by my advisor, the only person in physics that I ever called professor, okay? A great man, and a really kind man. The basic idea is that why is the pion approximately light? Because there's a limit where it's massless, and in that limit, it's an excitation around a symmetry direction, okay? And this is often called a Mexican hat potential, but a Mexican student of mine once pointed out to me that it should be called an American tourist hat potential, which I think is much better. But anyway, so this is that kind of potential, and so this potential is flat, okay, and this is obviously an extremely executive summary. The pion is an excitation around this thing, and so once it's massless, it's easy to make it light. You just tilt the hat a little bit, okay, and then it's no longer exactly massless. It oscillates around the minimum, but that can be a very long time oscillation. That's the basic idea. And if you ask, at the level of the effective Lagrangian for pions, why can't I just write down a pion mass, right? Remember I said, for the Higgs, nothing stops me from writing down this term. Well, it turns out that if you work this thing, you see that there's a shift symmetry here, right? There's a symmetry under which the pion field shifts, and that's why this is forbidden, okay? So the idea of the composite Higgs is, well, let's just copy this for the Higgs. Can the Higgs be a pseudo-Nambu-Goldstone boson, okay? And the short answer is yes, but. There's a but because the thing is that this shift symmetry of the Higgs is broken by, for example, the Yukawa couplings, or the couplings to the W's and Z's. So just like supersymmetry, it's not a symmetry of the standard model. If we want it to be an approximate symmetry, we have to introduce new particles that engineer this approximate shift symmetry in the UV. So it ends up requiring partner particles, not the same as, but conceptually similar to the way that supersymmetry does. And once again, these things can't be too heavy. I've already gone over my 5 minutes. One slide on anthropic selection. This is the idea that there are many vacua, many vacua in the universe, and we just happen to live in one of them. It's pretty random. So now, if we do this, we can imagine that in each one of these local minima here, the value of the cosmological constant and the Higgs mass squared, which are the two relevant parameters in the standard model, they're the ones we don't understand, okay? And we just ask, what happens as we move around from here to here, okay? What happens is that for the cosmological constant, if it's too big, we have a universe with no galaxies. It just expands so fast that it pulls galaxies apart. We have no galaxies. It's a pretty nasty place to try and live. If it's too small, we just collapse. The universe just collapses right away. There's a tiny little thin band here where we can have a nice, big, slowly expanding universe. What about the Higgs mass? We again find there's a very sharp boundary. If it's too big, we don't get nuclei. If it's too small, we don't get atoms. This is a little more complicated to explain, okay? But I don't have time to do it now, but happy to talk about it afterwards, okay? Obviously, where do we live? We live here, right? And there's a tiny region in these units where this is like the Planck scale or the string scale. There's a tiny region where we can live here, okay? So how is this an explanation? The way it's an explanation is that you can ask the question, of all the places in the galaxy or the universe, why did life evolve on the surface of a planet? Of all places, like what are the chances? Well, the answer is obvious. The answer is, well, it's the only place it could have happened, okay? So the fact that we find ourselves on the surface of a planet is not a mystery. And by this logic, if you can call it that, there's no mystery. This is the only place in the multiverse we could live, okay? So this kind of thing makes a lot of people unhappy. It kind of makes me unhappy. It keeps me up at night. But I don't think that means it has to be false. Maybe the universe does work like this. Maybe we're asking the wrong questions. Maybe the old school quantum field theorist is right, that there's no rational explanation for the parameters of the universe. Okay, that's it. I'm done. I'm only 10 minutes over. I apologize. I sincerely do. Thank you for being patient with me. These are my summary. I've basically said it, so I don't need to say it again. We need scale hierarchies. If we don't have them, we can't predict anything. Standard model is beautiful if we assume scale hierarchy, but we can't. It makes it very hard to understand the Higgs. So I think it's essential that we keep exploring, even if this problem is not going to be solved by my generation, maybe not even by your generation, but I think we should keep exploring. Thank you.
More questions? Oh, okay.
Go back row.
Can you go back to the slide where you showed the star on the edge between the two?
This one, the one with this one?
No, with
I think I know
sort
which
of
one you
hill.
mean. This one.
Yeah, I didn't understand. Isn't the Higgs mass supposed to be 0 on one of the two?
Ah, okay. So this goes back to, see, there are two notions of oops, where did it go? Sorry. I love doing this thing of builds, but then it makes it a real pain to, here we go. This is what I wanted to show. Okay. So, so there are two things that are the Higgs mass. One of them is this little number, which is the experimentally measured number. But that's very, very different from the parameters that appear in the gut model, in the fundamental theory. In fact, the MH of the gut model is this huge number. It's almost exactly the same as this number. Okay? So what I was plotting on that plot were the fundamental parameters in the gut model. Those are exactly the analogs of the doping fraction for the condensed matter system, because God or whoever is, the string theory is adjusting those parameters. Those are the parameters of the UV model, okay? And so I claim I'm really not cheating in this thing right here. This really is the parameter that you would have to put into a computer to compute the Higgs mass, okay, from the more fundamental theory, and it has to be adjusted to be within 1 part in 10 to the minus 26 of this phase boundary, okay? So that's not actually right. So because if so, a potential where the Higgs mass is 0, it looks like this, okay, and a potential where it's not 0 looks like this. This is the potential. Okay, so here the minimum is non-zero. Okay, but the physical Higgs mass is the curvature of this minimum here. Okay, so in both of these phases, it's away, if I'm a sizable distance away from this phase boundary. In both cases, this oscillation scale is what I'm calling m little h, okay? This m little h is 10 to the 15 GeV, order of magnitude.
I'll think about it, thanks.
Yeah, so I claim this is really just like if this thing star was in the right place, if you go either a little to the left or to the right of it, even by a little bit, the correlation length is just 1 lattice spacing, order 1 lattice spacing. In exactly the same way, the correlation length, which is basically the inverse, this really is the correlation length if you compute a 2-point function. This MH is the correlation length, and it really is this tiny little short distance scale set by the gut physics. I swear this is legit, okay? I'm not lying to you, okay?
So I just want to understand predictions of effective field theory. So are you saying about the thing about the electron, are you claiming that effective field theory predicts that all fermions should have small mass?
No, I'm just saying there's no problem in them being small.
Okay, but
There's no
it's not a
evident problem.
prediction.
There's an evident problem here in that we have to tune extremely close to a phase boundary, and if I mess this up by 1 part in 10 to the minus 26,
understand.
I double the Higgs mass. If I mess up the UV value of the electron mass in this theory by 10 to the minus 26, I mess up the electron
No,
mass by
I
1 part in
understand.
10 to the 26.
I understand. So,
That's the difference.
yeah, can you tell me, is there any specific prediction coming from effective field theory for any of the parameters in the standard model or any other model that you can tell me?
So if you want to say, I want to use the effective field theory to predict what string theory says,
forget about string
I
theory.
can't.
No, forget
No,
about string theory.
but I'm saying effective field theory is we're working from the bottom up and trying to parameterize what's allowed. To predict things, we need a more fundamental theory.
Okay, I understand.
That's the universality versus reductionism.
And-
If you need to have an idea for the fundamental physics to predict it, if you want to predict what the doping fraction is, where this phase transition goes, you have to look at the atomic physics. You can't
understand.
get it from the effective field theory that describes this phase transition. And the same thing is true in the standard model.
Okay, I understand. It's just the two philosophers that are talking. I just didn't understand exactly what the effective field theory person is supposed to be saying.
The effective field theory person is saying that I would like to have a rational explanation of why the Higgs mass is of order what it is, okay, or what it is, and there doesn't seem to be any hope for that in this framework.
Okay. Okay, thanks.
So yeah, thanks for the presentation. There is a slide that you said that the lambda QCD is 2 orders of magnitude below the W mass, you came with a reason for this, which I understand. But I also think that like if you start from a very high energy, like the gut scale, then you run down, then it's very surprising that lambda QCD is so close compared to that scale to the electric scale.
That's a valid point. That's true. This is something that we don't understand, okay? We don't understand. It's true that on the sort of logarithmic scale where we are thinking of grand unification or gravity, on that sort of a scale, it's true that lambda QCD and MW are quite close, and we do not understand that. Similarly, we don't understand why today the dark matter density is only a factor of 5 away from the ordinary baryonic matter density. There are many things like this that we don't understand, and I'm not trying to say that it's not interesting to talk about them, okay? So I hope I didn't give that impression, all right? But I just wanted to focus on this problem because I think it's a different sort of a beast, and yeah, I just wanted to highlight this.
Yeah, thank you.
Well, thank you for the lecture. I want to know more about the partners that you say on the composite Higgs. Which characteristics need to have to solve this problem?
I really think I would be very, very happy to talk with you one-on-one on that, but I just really don't think that's a question that I can give a short answer to, okay?
Okay.
So I'm here till Friday evening, so I'm around. If I'm not lecturing, which I seem to be doing almost all the time while I'm here, but I'd be very happy to talk to you about it, okay?
Okay, thank you.
Yeah.
Hi, thanks for the talk. I think I just didn't get something. Sorry if it's a dumb question. It's just because, again, in that figure, I don't understand why this is different from the usual renormalization program. Like, we don't do that for all the particles. Like, at some point, this is like the bare mass, and we need to kind of adjust to fix the infinites that we have, and then we have the mass or the parameter, the real parameters that we measure. I know that is related to that. In the fact of the Higgs, we have this, it's dependent of this new scale, of this new particle, but like just looking to this figure, I don't quite understand. For me, this is argument. It seems like it's just the usual renormalization program.
Well, it's true that if you sit exactly here to an accuracy of 10 to the minus 26, you have a completely consistent quantum field theory with a correlation length that is 26 orders of magnitude larger than the lattice spacing. And that can be described by an effective field theory, a renormalized quantum field theory, just in the way that you would describe. So would you say that means that it's perfectly fine to find this lying around? We have one universe, right? And it's this.
But it seems for
It's
me,
like this. It's
but
like
it-
you have one sample
but
and
it
it ended
seems
up
for
right
me that
here.
is more
You think
related-
that's okay because you can renormalize it?
Yeah, but it seems for me that is a problem with renormalization. Like we don't quite, it's not something that is.
Renormalization is a completely technical thing. If I want to
Yeah.
understand this quantum field theory, I have to renormalize. So what?
Okay, I think I
It's
need
just a
to-
technical thing, right?
yeah, I
The
just-
fact is that there's a physical scale, which is the lattice spacing. There's a correlation length, which is 26 orders of magnitude larger. The explanation for that is that I've chosen some incredibly special point in parameter space. And if I mess this up just a tiny bit, the qualitative physics completely changes. And renormalization is just some technical tool that helps you to see that. And it's exactly
okay,
the same thing. Whoops, oh, I'm very, very sorry. I hit the wrong button. So the claim is that the gut theory is qualitatively is exactly the same way. It's a physical scale. There's actually stuff at the gut scale that we could go up and measure. And then we could try to predict the Higgs mass, and it would look just like this lattice thing. We would find that we're insanely close to a phase boundary. We have to do a 15-loop calculation to find that out, 14 loops.
Okay, thanks.
Okay.
Thanks for the presentation. And I was just wondering, you know, the cosmological constant is also a very small number, and you can always add some constant there, so you have infinite contributions, but in the end, it's very tiny. So it seems, it always reminds me of the Higgs
Yes.
mass. So is there any model, are there any models that propose to say, oh, these two scales that sets everything, actually, you know, the solution,
Yeah,
is there a solution for both of them instead
Yes.
of just the Higgs or cosmological
I told you
constant?
what it was.
Oh, and
It's this. Okay? No, I'm not
Okay.
joking. I'm not joking. The thing is that, of course, many people have tried very, very hard to find solutions that are perhaps more analogous to the supersymmetry and composite Higgs to solve the cosmological constant problem, to explain why it's so small from a more fundamental perspective. In fact, supersymmetry takes a pretty big step in that direction because it turns out that the cosmological constant can be naturally zero if you break supersymmetry. So you start getting very excited, yes, yes, yes. But then you find out by the time you've broken it enough to explain the fact that we don't see, say, scalar electrons or scalar top quarks, then you've broken it so badly, you've now reduced the fine-tuning problem to some, like, 20 orders of magnitude or so, rather than 50. So you've made some progress, but you wouldn't say you've solved it. And in fact, and then there have been lots of nutty models, okay, which don't work. And this, even though we might hate this is like the only game in town. And so this is one of the reasons that this keeps me up at night.
yeah, it's very
You had to
disturbing.
ask.
Okay. Maybe the most philosophical part of the discussion could be over coffee. So if there are
Coffee
no
or
more
maybe even
questions,
wine, I don't know. Maybe
let's,
tonight.
yeah, this one more like wine. Yes.
Yeah, this is
So
a
let's
wine
thank
discussion maybe.
the speaker once again. Thank you, Markus.
Thank you.